Shall I start?
Yep.
Right. Welcome, everybody. Thank you for coming to my talk. So my name is Michael Perikas. I'm an associate professor at Chalmers. I thought I'd maybe start by saying a few words about myself, because I guess most of the people don't know me. So I'm from Barcelona, and I actually did a PhD at the EuPC while I was working at Barcelona Supercomputing Center. So my background, or what the work that I was doing at my PhD, was mostly in the field what we call computer architecture. So it was mostly design of microprocessors and trying to find novel organizations for designing high performance processors. So I was working at BSc also at that time. So, and I have an interest in HPC and supercomputing. And I also spent, after working for BSc for a few years, I went to 2 years to Tokyo. I was at the Tokyo Institute of Technology, where they have this supercomputer, which is called Tsubame, or the series of supercomputers there. And at that time, I started working more in topics related to programming models and analysis of runtime systems, performance analysis of runtime systems. And after that, in 2014, I moved to Chalmers. Chalmers is in, for those who don't know, Chalmers University is in Gothenburg, which is a city on the west coast of Sweden. And I've been there now for 10 years, working mostly on topics related to programming models and co-design. So at Chalmers, we are involved in several European projects that are related to RISC-V, and one of them is this EUPILOT project. So I got an invitation from Kenneth, for which I'm very thankful, to provide our experiences, to talk a little bit about what's going on. So this is how I've organized the talk. I will start a little bit talking about RISC-V and what's the interest of the, let's say, European Union in RISC-V, and mainly focuses on two very linked projects: the European Processor Initiative and the other project which is called EUPILOT, which I will present in a bit more detail. And then I thought, okay, since I give the chance to talk to you, I want to also talk a little bit about the work that we are doing at Chalmers. So I want to talk a little bit about some research directions here that we're pursuing. And finally, I'd like to share some thoughts about my general feeling about where we are. I mean, where RISC-V, let's say, is in the context of in HPC, and what needs to be done. So before starting, I'll just like to ask a general question. I mean, how many of you have heard about RISC-V? Okay, I guess that's most of the people. That's a good sign. I'm not going, I mean, I'm a teacher, but I'm not going to ask you now to go out and try to define what it is. So, which is what I would usually do, but then we would need many hours. So, but anyway, I think I should probably try to provide some introduction into RISC-V. So, RISC-V is an open instruction set architecture. It's based on the RISC philosophy, and it's very much unlike other ISAs that you have probably very familiar with, such as x86 or ARM, in the sense that it is an open standard which is not under the control of a single company. If you don't know what an ISA is, well, ISA is basically, you can understand as the language that the processor understands. So x86, ARM are well-known ISAs or ISAs. Now, in open in this context means that it is freely available for everybody to use and also to modify. And I'll come to that also in a moment. And many people think that RISC-V is an open source processor, but that's not true. RISC-V is an open standard. It's open source in the sense that the sources for the ISA are open. Now, the advantages of having such an open standard is that, well, you don't have to pay royalties to any company. If you want to make use of this ISA, you can. It enables higher customization. And as a vendor, if you implement a processor that makes use of this ISA, you can benefit from the fact that there's already a shared software ecosystem. But I put here into parentheses that this, of course, depends on the fact that you have to adhere to the standards. So in a sense, this bullets of customization, that's a good thing. But if you are going to customize some parts of the processor, make extensions, your own extensions, you will have to develop your own software environment for that, of course. And of course, there's it's a great community, very vibrant community, and a lot of people have a lot of interest. So it's easy to reach out and get support. Yeah, I mean, yes, I'm totally happy. It depends on.
When you say about the customization, are you able to customize it in the sense it's like a GPL thing that you have to give it back the customizations, or you can do proprietary ones for yourself?
No, you can do proprietary ones. In fact, they are, yeah.
Okay.
You will see that vendors are all the time doing this.
Thank you.
Okay. Now, as you saw in the title, in this talk, I want to focus a bit about the European perspective of RISC-V. And you might have noticed that RISC-V appears often when in the context of the EuroHPC joint undertaking. So in this slide, I actually tried to take some different views from various sources, but one of them, actually the whole slide is not visible, so I'm not sure if, maybe if I click, it's going to disappear.
Click the Alt twice. Yeah.
Twice? No. So now it's visible, but it's still with the bar there. Well, I just want to point out that there is in last year's RISC-V Summit Europe, there was an interesting panel exactly on this topic. So if you want to go into more detail than what I discussed in this slide, you can actually go and look into what all the panelists had to say about the topic. But one important reason that the EU is interested in RISC-V is that it wants to achieve or develop an autochthonous HPC industry. And we're actually seeing this trend in many regions on the world, and many governments that feel that the way that the semiconductor supply is currently organized around a few select companies and a few foundries, it's a bit of a risk situation. There's a chance that you might get cut out. So many governments feel that moving towards an open standard provides a higher security and less risk. So there's an interest in developing our own HPC industry. Then there are also needs such as, interest in increasing HPC capacity, development of HPC skills. And also, some people would like to see a movement towards open source hardware. There's a bit of a debate at this. So the vision is that, okay, up to like the Linux kernel from the software stack, we have a lot of open source software, but below the kernel, it's mostly closed. So it would be nice if we can also have open source hardware. There is an open source hardware movement, but there is some debate as to how viable this is. Particularly, one important concern here is that unlike software, which basically compiling can run on your system, if you want to do open source hardware, if you want to actually tape that out in, let's say, high performance node, that has a huge amount of cost. So somebody will have to pay for it. Now, why is there interest in RISC-V specifically? Well, it's sort of because none of the other options actually fulfill the requirements. As you know, x86 and ARM are controlled by entities that are non-EU entities at this point. And that's actually, if you watch look a little bit at the history of how this has developed, a lot of people track this development of like these EuroHPC projects now back to a series of projects that was called the Mont Blanc projects at the BSc. And those projects were based on ARM. They were starting with ARM, let's say, embedded, I might say, or processors that were originally designed from smartphones to try to build clusters based on ARM technology. But then, you know, at some point, SoftBank bought ARM, and well, still under control of SoftBank to an extent, as I understand. And then the European Union felt like, okay, you know, we've been doing all this investment into technology which we actually cannot control. So that's one of the reasons that they suddenly start looking into RISC-V. Then also, you can see that RISC-V can be a language to somehow communicate academic ideas with industry. All right, and well, this last bullet here is basically what I mentioned, that RISC-V is an open standard, doesn't mean the same as open source hardware. Okay, so you probably heard about the EuroHPC joint undertaking. So here's a definition which probably I took from their own website. It says it's a joint initiative between the EU, European countries, and private partners to develop world-class supercomputing ecosystem in Europe. They are funding several different initiatives. On the one hand, they are funding big supercomputers for use by researchers. There's a long list of them. I think the largest of them is currently is the Lumi supercomputer in Finland. But there's also a side of research and innovation projects in which we happen to participate in a few of them. There are many of these projects, but 3 projects which are related, in fact, to RISC-V and where hardware design is important is the European Processor Initiative. This is sort of the project which I would say kicked off a lot of this work. This project had two goals. One is to develop an ARM host processor. So the ARM is still in the picture here, and also an accelerator based on RISC-V technologies. In fact, it's not a single accelerator. There are several accelerators. This is usually called under the name of EPAC, and which I think stands for European Processor Accelerator Chip. There are 2 ongoing pilots also now, which I will actually show in the next slide a bit, which is the EUPILOT and the EUPEX. And there's also another project which I will not be focusing so much about today, which is called eProcessor, which also has the goal of developing a RISC-V-based processor with extensions for doing HPC and for executing bioinformatics applications. So let me show you some slides which I actually got from a presentation from Filippo Mantovani. He's one of the researchers at Barcelona who is involved in the development of the RISC-V accelerator. And I want to show you 2 slides, which this is from a seminar that was in fact in Jülich last year. So to show a bit what is being developed in this EPI project. So on the one hand, we have an ARM-based general purpose CPU, which is called RIA. And you might have heard about this because, as I understand, one of the partitions of the Jupyter is going to be based on this technology. So this is mostly, developed by Cyperl, which was a company actually funded within EPI to sort of drive this development and commercialize it. Then on the other side, we have this EPAC, which is actually a set of accelerators, but the one that is most interesting to us, I mean, Chalmers, and also to me and related to this talk, is basically a vector processor that is being developed inside of this project. And this is called EPAC. And why I show this, because I want to sort of show this timeline. And in fact, in this timeline starting 2015, you see also this Mont Blanc and the Deep projects appearing here. You will see what is sort of the strategy of the development. So we have the EPI project, which has in fact 2 phases. And these phases are developing these 2 processors, the ARM-based host processor, that sort of feeds into this EUPEX project, which is a pilot to develop a system based on the RIA chip, and another pilot to develop a system based on the EPAC chip, and that's the EUPILOT project. And the idea is that the outcome of these projects will feed into future exascale systems. So we already know that Jupyter will have some components based on RIA, and for the for the EPAC, there is a, well, I would say there is a wish that the next Mare Nostrum 6 will have a partition based on these processors. Okay, so since the topic is RISC-V, I thought, okay, I'll describe a little bit about what exactly is being implemented in the EUPILOT project. These slides are not mine. They are, so Carlos Puchol, he is the technical coordinator for the project. And so I'm going to be mostly showing a subset of slides that from a recent presentation that he delivered that was actually at high peak. Okay, so well, typical slide with where you can see all the partners involved in the project. We have a set of, well, a total of 19 partners. There's a set of academic partners. There's a set of industrial partners involved. For some reason, the figure on the right, I think that's actually taken from the EU portal, but it's only showing, I think, the location of the academic partners for some reason. But as you can see, it's sort of distributed among Europe. The project is coordinated by BSc. And well, here in Sweden, we have Chalmers, and also KTH is also participating in the project. So what are the goals of the EUPILOT project? So first, the main goal is to demonstrate this pre-exascale accelerator platform. So we want to actually deploy and show the a RISC-V-based accelerator platform that is in a usable state. And to reach there are several things that we are working on. On one hand, the project is, well, designing and doing all these validation steps and deploying the accelerator platform with a goal of maximizing European technology and assets, because that's always one of the goals also of the EuroHPC. There is the project goes across the whole stack. So there is a goal to do software and hardware co-design to sort of, to basically drive the hardware design from the software components with the goal of improving performance and achieving better energy efficiency. Then finally, also, there are the goals to extend open source into hardware for HPC. Some of the components that are being developed will, in fact, open source, or some of the hardware is open source, and to do everything based on the RISC-V instruction set architecture. So this is a top-level view of what we're trying to build. It actually has two types of accelerator chips that I will describe in a little bit more detail next. We want to integrate 8 of these chips into an accelerator board that will then be connected to a host server. And all this goes into this tank. So it's going to be using immersive cooling technology. And there's already a space at the BSc where this is going to be installed, as I understand. Okay, this is a sort of high-level view of the system. And here's a bit more detail on the actual chips that are being developed. So there are actually two chips that are both sort of derived from this EPAC chip that I mentioned that had several accelerators. So out of these accelerators, here there are 2 which we are going to construct discrete chips out. One is a vector accelerator, which in fact combines a core that is developed by a company called Semidynamics that is also located in Barcelona. So they have a core. They are designing an out-of-order core called Atrevido. And this will be connected to a vector processing unit that is mostly coordinated by BSC, the development that implements the RISC-V vector extension 1.0 standard. And on the right side, we have another chip here, which is called the MLS accelerator. MLS here stands for machine learning and stencil. This is, well, as you, this is designed mostly for AI type of applications. We are not so much involved in this work, so I'm not going to be discussing much about the parts related to the MLS in this presentation. At the end, the goal is to tape this out in technology. So it's 12 nanometer global foundry. So this, as you can realize, is not the most cutting edge technology. But you know, if you wanted to implement this in, let's say, like 5 nanometers, the cost of the project would explode. I mean, it's not like going to one of the high performance nodes. It's not an incremental increase in cost. In fact, it multiplies the cost by, well, probably by more than an order of magnitude. And this is the software stack that we are working on. So the way that this project is organized is that we select a set of applications, of target applications, and then develop the underlying stack to try to make that work. And here we have on the left side the components that are targeting the vector accelerator. On the right side, we have the components that target the machine learning stencil accelerator. So in terms of applications, so the main targets that we are looking at is GROMACS, which is mostly developed and coordinated by KTH, by Professor Erik Lindahl. And there's also EC-Earth, which I understand is being developed at BSC. And you know, basically a stack of many libraries and tools all the way down to the system, Linux, and also, of course, the tool chains to compile the applications there. So that's one of the efforts that is ongoing, and that, of course, is a critical component of the system. So at the end, what we are trying to achieve in terms of performance is shown in this slide. So, of course, one thing that I have to point out is that whenever I'm showing numbers here, this is sort of subject to constraints of budget, and some, you know, the cost of a square millimeter changes over time. So depending on variations, some of these numbers will change. But the goal for VEC is to develop let's say a 16-core chip in an area of 46 square millimeters, and such that each chip has 8 vector processing units. And if you do the math, for example, considering that the fuse multiply add counts for 2 flops, then for a 64-bit floating point targeting 1.5 gigahertz, we reach to 384 gigaflops per chip. That's not counting the double precision of the core itself. So in total, that goes to 432 gigaflops per chip. And since we want to have 8 of these chips on a board, so we hope to deliver a system where each of these accelerator systems, this EUPILOT accelerator system, each one delivers about 3.5 teraflops. Now, I talked a bit about the work that is being done in the development of the applications and the tool chain. So one of the critical components that is required to make this work is what we call the software development vehicles. And so you can think of it as follows. When you start developing a processor, you want to start immediately developing also the software that is going to run there. But of course, at that point, you don't have any hardware to actually develop the software on. So what is the solutions that you can go for? So in The EPI project and also in the EUPILOT projects, we are relying on several options, several platforms. One, this is the, let's say, the hardware prototype platform that we're using there as a software development vehicle, which consists of two type of platform, two types of boards. One is taking, for example, a set of RISC-V commercial boards. And in this case, we have a series of boards from that are this Hi5 unmatched. That's a board that has a series of chips with 4 RISC-V cores that we can start to use to do some software development. Of course, this is not the same as the chip that is being developed. We do not have, for example, the vector units here. So in order to be able then to target the vector unit, you need to do something else. One option is that you can try to emulate the vector instructions here. So there's, for example, a tool which is called behave, when every time that you run you execute a vector instruction on a platform that doesn't have support for vector instructions. So what happens is that you get a signal, right? You will get a signal ill instruction, the signal, something. Well, this tool captures the signal and then goes to analyze what is this instruction and sort of emulates that in software. That's one option, and you can do it. Or another option is that you can actually try to run it on FPGA itself. You can try to put the RTL, meaning the hardware that is being designed, compile that, but instead of targeting to the, let's say, the tool chain for taping out the chip, you target an FPGA device, and then you can map it on FPGA, and you can try to run your whole software stack, meaning that you can try to boot Linux here, and you can try to run the whole tool chain and test your applications there. This, of course, getting this to work is a major effort. It requires, to develop the hardware itself, to actually get all the operating system to boot there. So, and then of course, you might not be able to emulate the full system, because in an FPGA, the density of hardware, let's say, that you can emulate is not the same as the one when you tape out. So here, for example, you could have maybe a few cores without the vector unit, or you can have maybe just one core with the vector unit to try to start working and developing code there. Later on, I will also mention there are some other options. You can also, for example, try to do RISC-V development in purely virtual environments. So I will also discuss a little bit about that there. So this is a little bit what I wanted to explain about the work that is currently being done in EUPILOT. So the next thing I wanted to talk a little bit about our involvement and sort of a bit of what projects we are working on at Chalmers. But maybe I'll take a break here just to ask if there's any questions on the topic so far. Okay.
Maybe we can get back to it at the end, but what's the biggest challenge in these type of projects to actually get to the point where we have, say, a European supercomputer running on only RISC-V, so CPU and accelerator?
Well,
I mean,
there are many challenges. So the question is, what is the major? Well, I think, the development of the hardware and its verification to make sure that it can run, that it can reach the stability to actually run software, that is a major step. And I think it's really like when you reach that point, it's really like a breakthrough, because at that point you can then start more productively developing code, and then actually try to start to optimize it. So I was thinking actually about this a bit while coming here, that it's like, I can see that they're like this, basically it's two important phases. One is to try to get, to your first version, to get that working. And then after that, you basically have to start an iterative process, because now you want to optimize the software and you want to optimize also and to improve the hardware. So you start developing your software, targeting this new hardware, maybe using some performance tools. And then you can try to optimize get the feedback from the performance tools to optimize your software. But at the same time, you provide new information to the hardware. So a new version or improved version, hardware improvements are developed. So now you get to a new version of the hardware. And now there's a question about, okay, these optimizations which you did, how portable were they? Do you need to now re-optimize your application? So at some point, then we get to this point. And that's why, I can see that the road towards getting this to work is probably still, a few years ahead. We are now sort of, I think, reaching this point where we do have some platforms. I mean, I'm talking a little bit about these projects now. I mean, there are many approaches. In fact, I will talk about what some other vendors are proposing. But what I can see in the projects that we are involved is that we are getting to a point where we do have working hardware. And now I think we need to start with more actively with see how we can do sort of, iteratively learn from attempting to optimize applications, seeing, which are the instructions that they most rely on, what optimizations should be introduced into the hardware, then try to develop next version of the hardware, and then see, okay, now can we start again the process of looking how well these ported applications are going to run, and eventually we'll reach there. And this is a step that something that will require certainly a few steps until you reach there. That's why I think in any of these projects of this scale, it's not really realistic to think that, we're going to develop the chip and immediately the chip will be competitive. No, you develop the chip and then we have to start. And after a few generations of the chip, then we hopefully can reach to something that will be competitive. That's the way I see it. All right. Okay, let's talk a little bit more about our involvement, what we're doing in Chalmers. So we do have two parts. We're working a little bit on the software side and also on the hardware side. So on the software side, we have been looking at vectorizing convolutions, for example. We have also been looking at how to optimize parts of the OpenMP runtime there. And we have also planned this, we haven't started yet, to actually work on having an efficient implementation of SYCL for RISC-V. And it's interesting because there was a discussion about SYCL also before. And this is sort of interesting, because if you think about how many applications there are out there written in SYCL, actually the number is not that large. But one of the reasons we are interested, or there's interest to get SYCL to work on this, is because SYCL can serve as a sort of intermediate step when you are porting applications from CUDA to work on this platform. So that's one of the things that we want to look at also. And then on the hardware side, I'm not going to talk about these things, these two topics, but Chalmers is sort of responsible for what is known as the home nodes. So to basically ensure that the cores are going to be cache coherent, both within a single chip, but also across different chips. So that's one of my colleagues are working on this part, but I will not be discussing this into detail. So in the next few slides, I want to talk a little bit, provide some example of activities that we are working. This is sort of my day-to-day life. So I hope that I can make it interesting and not just bore you with a lot of technical detail here. But to jump into that, I want to talk about one thing, which is the RISC-V vector extension. And the reason I want to talk about this is because I think this is one of the important developments that has happened in RISC-V over the past years that is an important step towards being able to have high performance computing in RISC-V. So you're probably aware of what a vector extension is, because It's very commonly implemented. I mean, all architectures or major architectures have vector extensions. In the case of x86, you will have something, like AVX512, AVX2, and earlier you had the SSE extensions. In the case of ARM, we have the Neon instructions, but there's also the SVE, the scalable vector extension. So, and all these are very important to achieve high performance, because vector execution is one way to also achieve good energy efficiency. And why? Well, basically you can think of it as when you have vector instructions, then you are able to decode one instruction, but the semantics of the instruction itself indicate multiple operations to be performed. So you decode the instruction only once, you schedule it only once, but then you can execute many operations, and there's a guarantee that those operations are independent, so you don't need to do any, let's say, disambiguation at the hardware level, which is something which is a bit costly. So that's why also the approach that we're taking in EUPILOT and EPI to try to achieve high performance RISC-V execution is using the vector extension. And in fact, so this RISC-V vector extension, there are several versions of it. The 1.0 version, let's say the standard 1.0 version, was ratified towards the end of 2021. We are leveraging it in the EPI and EUPILOT project. So I put here both this EPAC and VEC, but it refers to basically these two projects. And one of the major strategies that we are attempting there to try to increase as much as possible the energy efficiency is that we are relying on having very long vectors. So one thing that I haven't mentioned yet, but it's actually the next bullet here, is that the way that this vector extension is built, it's also similar approach taking in the ARM SVE, is that the architecture itself doesn't dictate the length of the vector register. This is unlike an extension like AVX512, which says, AVX512 is for 512 bits. But in the case of RISC-V, you can have any size of vector register going from, I think it's either 64 or 128 bits up to 16,384. You can do this in increments of 2. So this number of bits, what does it mean? Basically, this means that you can have vectors of 256 double precision elements. And in fact, at the programming model, you can even make these vectors longer, because RISC-V supports something which is called LMUL, which basically allows you to take multiple registers and treat them as a single register. So the idea here is that we will be able to achieve higher energy efficiency by following this approach. Now, this is enabled by having this programming style, which is called vector length agnostic. So since now the implementation is free to choose the actual length of the registers, it means that when you are, for example, processing a long vector, an application level vector in a loop, then when the compiler generates the code, it will have to do some extra bookkeeping, trying to understand first, okay, how many elements can I actually fit in the vectors that are available, and then partition the loops in as many iterations required to actually be able to process this loop. So this provides some portability, but potentially there are some scenarios in which you might lose some efficiency by doing this, as compared to what would be called a vector length specific code generation. So the way I like to think of it is, can we basically do something that is competitive with a GPU by using long vectors? And a bit of the research that we do goes into this direction. Now, before going to that, I just thought, okay, another sort of important consideration when you are talking about vectorization is, how do you actually vectorize? Because this is this is a big topic and something that actually has been studied for a long time, and there are many challenges. So let's say the two extremes that I have here on this slide are, I think, the easiest to understand. One is, okay, you do everything. Well, you just code your program in assembly language. You have maximum control of all the features. This is, of course, not very productive. On the other extreme, what you would like to have is something where the compiler does everything. This is usually called auto-vectorization. But here you give all the control to the compiler, but this would be the most productive. Unfortunately, you cannot always rely to auto-vectorization. First, auto-vectorization requires the compiler to be able to do analysis of, let's say, memory addresses and dependencies between instructions to guarantee that, for example, when you are looking at a loop that is, for example, adding 2 vectors and storing it to a third vector, you would require, for example, to guarantee that the output vector cannot alias with any of the input vectors. If you cannot do this because the programmer has just written some pointers there, then the compiler must say, I'm sorry, I cannot vectorize this. Otherwise, it might be wrong code generated at the end. So, and there are many other scenarios and small details that may cause a compiler to fail in the vectorization. So there's a lot of work also required to try to get this technology to work effectively. And sometimes we will have to actually ask the programmer to help a little bit, which is something that you can do sometimes easily by adding some SIMD clauses. Like in OpenMP, you can do something like pragma OMP SIMD, and then you tell the compiler, there is no dependencies in this loop, you can vectorize this. So the compiler say, okay, thank you. But reaching this, of course, if you don't have a vectorizing compiler, just getting to this point is a big effort. So one of the things that we often that we do is some intermediate step, which is the program using intrinsics. This is a way of programming which still gives a lot of control to the programmer, but it provides some help of make some things, simplify some tasks for the programmer. So I don't know, have you ever programmed using intrinsics, for example, for x86? Okay. Yeah. All right, then you know that, for example, when you program with intrinsics, you don't need to worry about the register allocation, and you can make use of the access variable names directly. So this will be something that will be helpful. So actually, in the EPI project, a set of RISC-V built-ins has been developed to target most of the RISC-V vector instructions, but not all of them. And they have some format like, will be called built-in EPI and the name of the instruction, and with some extra parameters there. But so, and this has sort of been a way to prototype, to try to develop a first set of intrinsics to make this work. And later on, the RISC-V Foundation actually has set up a task group to come up with standardized RISC-V vector intrinsics. And now there is a standard. You can see, actually, I just put 2 instructions like vset vl, so set vector length with the EPI built-ins and with the name of the standard. So you will see that format is a little bit different, but it's basic, but they are equivalent. There's a frozen spec now, but it has not yet been ratified. So this is not yet standardized, but there is implementation of in GCC and LLVM are ongoing here. These are sort of the 4 major ways that you can leverage a vector, the vector extension. And in fact, any new ISA extension, before it can be fully be used by the compiler, you can work at the assembly level, or you can try to develop some built-ins for it. So the one thing that I haven't mentioned here on this slide is that when you are doing assembly, there is also an option to actually generate the assembly at runtime using just-in-time compilation. And I will come back to that a little bit later, but this sort of enables more optimizations. As long as the more information you have about, let's say, variables and the runtime state of your program, the more you will be able to optimize it specifically for the platform on which you are executing. So there's also several approaches that are looking into being able to, for example, generate or JIT generate vector instructions. I haven't been checking the time, but
you started late, so let's say half an hour.
Mm-hmm. Anyway, let me just then show a little bit, just to highlight a few of the things that we are doing without going into too much detail. We'll talk about the project. So this is a project in which one of my PhD students, who actually started as a research engineer in EPI, she was looking into how can we make use of the vector units to try to efficiently or to make efficient convolutions. And well, in particular, she started early with her work. And in fact, at the beginning, she was working on RISC-V, and she was working on a few different approaches. So let me actually backtrack here and say that when you want to run, convolutions, like convolutions that you would do for machine learning, actually there are many different algorithms that you can use. You can do what is called a direct convolution. You can apply an algorithm which is sometimes called IM2call gem, where you do a transformation of the input matrix so that you can use a matrix multiplication later on. You can also use an algorithm which is called Vinograd. And finally, it's also possible to use FFTs for convolutions. Now, FFTs are not that commonly used. I think they have some, for the sizes of the kernels that are usually used there, they sometimes lead to numerical instability. So most of the approaches are based on either direct, IM2call, or Vinograd. And Sonia had developed an implementation of the Vinograd for RISC-V, and she set out to try to port this work to RISC-V to see what are the challenges of taking a code optimized for RISC-V and try to get it to run on a RISC-V platform using the vector extension. So she set out to do this work while trying to maximize the usage of the vector units and of the vector registers. And also, because we are interested in doing some code design, we looked also into some hardware parameter tuning. So I was thinking, can I get rid of this slide? But at the end, I decided to keep it just to point out a bit of the tool chains that were used, and that this work was actually based on using a hardware simulator, which is called Gem5. So we did not actually run this on the FPGA platform at this point, but using a software simulator for the project, and also using the LLVM Clang toolchain, which is targeting RISC-V, which is being developed in the EPI project. Okay, so without going into too much detail, just to try to provide the high level that when you are doing a Vinograd convolution, you have to do three things. First, you have to take the input matrix and the kernel and apply some transformations. That's the first step. The second step is that you have to multiply these in a type of multiplication, which is called the tuple multiplication. And after you have done this multiplication, then you can convert it back. So in the original work that we did on RISC-V, we figured out a way on how can we try to increase the intertype parallelism, or basically make use of parallelism across different input channels in order to be able to fill vectors of longer size. So in this case, it's just showing how you can, for example, fill a vector of 512-bit using 4 channels. But I mentioned before that for the case of the VEC, we have very long vectors of up to 16K bits. So this approach would need to be extended. So the first thing that we did to try to use 32 channels in order to fill, in this case, up to 4,000 bits. So you already realize that this is already sort of hinting to one problem of using very long vectors, is that you will need to be able to find enough parallelism to be able to fill those vectors. In this case, we say, okay, we use the parallelism from different channels, but how many channels can you actually have in your application? So that was one of the approaches. The other was to try to increase the tuple size, or also to utilize longer vectors. So we started working, looking into how to port this to RISC-V, and we identified several challenges. And when you do this work, the thing is, you will probably be biased when you start from one code and then try to port it to another one, because here we started from RISC-V, and then of course the simplest way to try to port it is to say, okay, let's try to do one-to-one mapping. And then of course you will find out, okay, in my original code I used this instruction that was, for example, load quad word elements into a vector and replicate. And then when you go to the RISC-V vector spec, you might find that, oh, this doesn't exist. So you have to find some alternative. So, well, in this case, we found that we were lacking similar instruction that basically what this instruction would do. I don't know if my mouse pointer is visible. Maybe this is not the best, but it's to try to take a set of elements here and basically replicate them a set of times over the vector register. Okay, so we figured, okay, we could try to, for example, use index load to basically load these elements and then keep replicating them on a vector register, or alternatively, to use a type of instructions that is available in RISC-V, which is called slide up instructions. So we evaluated that. We realized that, okay, according to the simulated data, using the slide up instructions would be considerably faster than using the index vector load. Nevertheless, having a single instruction that could implement this would probably still lead to a faster execution time. Another challenge we identified is that we were, for example, lacking an instruction that would do a transpose of 4 vectors. So I guess this figure on the right shows this. You have let's say the 4 vectors organized in this row way, in this row-based way, a sub 0 until a sub 3 here, and after the transform, would like to instead have it organized, in this column way over a set of vector registers. So that's such an instruction exists for RISC-V, but we don't have any equivalent, for example, in the case of RISC-V. Interestingly, in the case of EPI, there is actually a custom extension, which is not part of the vector standard, but that targets only 2 vectors. So that was not something that we could, that was useful for us. So we tried several different alternatives, like doing a unit strided store, then followed by an index load, or doing a strided store followed by unit strided load, which more or less perform the same. At least these 2, because as you can see, they're basically doing the same operation, but just following a little bit different logic. But in any case, so we identified an option here to maybe come up with a similar instruction to further speed up this process. And the final challenge that we faced, that was both related with performance and also programmability aspects, is that it turns out that in the case of RISC-V, it is possible to declare a vector type at the C level and then take a reference for it. And this allows to well, this was allowing us to solve a problem that we had here, in which we were trying to, let me see, did I describe it actually on the slide? Okay, so the idea is that in the transformations, there are some operations that need to be done over vectors, and that they need to happen on every time that you are calling these three transformations: the input transformation, the kernel transformation, and the output transformation. But the registers, the vector registers on which we want to operate, they're not always the same. So there's a challenge that, okay, so if you want to, for example, create a procedure to do this transformation of the vector registers, then you would have to basically use a set of intermediate vector registers on which that would be used to pass the parameters to this function and then return the parameters, the vector parameters back. And that would, of course, well, that first of all would increase the register spilling. And furthermore, this actually reduced programmability, because in the case of RISC-V, such a passing of references is not possible. So we would have to actually write the code, which was about 30 lines of code in 6 different places in the program, so leading to decreased programmability. So that was, that's what we ended up doing. But we're trying to look into ways in which such a possibility to try to pass register references to procedures, if that would be possible in the case of RISC-V, it would certainly help very much for this type of scenario. So overall, without going into too much detail, we found that compared to the traditional approach that uses IM to call, the Vinograd implementation that we did on RISC-V was about 20% faster. And on the Gem5, it would actually achieve comparable performance to our optimized RISC-V implementation. So that was sort of a good outcome. And then also because we wanted to look into what is the actual efficiency of this and scalability, more in terms of co-design, to try to understand how useful is it actually to have longer vectors, or how useful is it to have longer caches. So we did this study in which we tuned the parameters of the L2 cache, for example, from 1 to 256 megabytes, and also the length of the vector registers from 512 to 4K. And what we learned by doing this is that in terms of vector length, there was not much point in going beyond 2K vectors. And also the performance, the impact of increasing the last level cache in this case was the second level cache, sort of saturated after 64 megabytes. Well, combining these two factors together, we predict that using an implementation that would have 2K vectors with 64 megabytes last level cache would achieve about 1.8 performance improvement. Yes?
But this is for a tiny network, yeah, for a VGG, which is minimal. If you have something bigger, did you try something bigger than that?
The other thing we tried is YOLO,
which is also tiny.
Yeah. No, so we didn't go for larger. One of the reasons is actually a bit related to the practicality of the approach. When you're using a tool such as Gem5, it's actually extremely slow. And if we go for a very long vector, that was not vector, so a very long, large model, that would not finish. In fact, for YOLO v3, we didn't, in fact, simulate the whole thing because it would simply not finish in a reasonable amount of time. But I'm actually interested in your suggestions for other types of network. Are you talking about CNN related or non-convolutional?
I would say, like, if you go for a transformer, it would be much bigger. Okay. Yeah. So those numbers will still keep continuing going down. Yeah, that's the thing.
No, I agree. I don't know. This is, yeah, we are very interested in looking into transformers. For a moment, I thought you meant larger CNNs. But no, if we talk about transformers, that's, it's that's actually, I would say that it's sort of future work. Okay, yes, but okay, so this work was done actually on a library which is called Darknet, which is not really that commonly used anymore. So one of the things that we are also working on right now, in fact, I have a master's thesis going on right now, is to try to put these algorithms like the Vinograd, the IM2call, or also an implementation of a direct convolution inside of one DNN. So one DNN is a much more well-known and or much more commonly used library for doing machine learning operations. And it's open source. It's actually was originally developed by Intel, so it's part of this one API stuff. But there's also ports for many other architectures, so you can use it also ARM, Power, and also there's RISC-V that we are actually developing inside of the EUPILOT project as well. I will not show you any performance results, but I want to show a little bit about what we are currently doing, because it's with one DNN we actually are making use of this sort of JIT approach that I was describing. So it's also a sort of an important tool to support in this ecosystem. In fact, the work itself on one DNN wasn't started by us; it was started by BSc. I think it's mainly Mark Casas and one of his students that has been working on this, and they come up with this. They implemented a JIT approach in one DNN. Basically, if you want to, for example, have generate an instruction, which in this case is a vector addition instruction. You can, from the high level, you will just call a function which is okay, push this instruction, and then later on you can generate the code and execute it. So using JIT has its pros and cons, I would say. Two problems compared to using intrinsics, for example. A problem is that you need to keep track of the registers manually, because here you are really actually specifying the exact registers that are going to be used. You cannot use high-level names that the compiler can then transform for you. And basically it's the same as creating an assembly version of your code. The potential benefit, well, in this case, is that this approach at least makes it easy to extend and to add instructions to a JIT. And why one would like to use JIT itself is, as I mentioned before, because you can, it enables certain types of optimizations. One sort of simple optimization you can think of is that if you have, at some point you want to, for example, call a convolution, for example, let's say you want to execute a matrix multiplication, and when you write your code for your matrix multiplication, you will have, you have, for example, so many rows, and we will have so many columns, and then we can come up with some blocking, but you have to sort of support a range of sizes. But if you do it on a JIT approach, at that moment, you might know that, the matrix I have to operate is exactly 128 rows and 64. So I can then propagate this information and simplify the control flow inside of the routine to create a specialized version to be executed at that point. So there are instances in which having some of these information which only when you are executing will allow you to generate more efficient code. So that's why we are interested into this. And I have here a couple of slides that just show a little bit how this approach works, but I think I'll just go quickly. I'll just sort of skip over it. Maybe I'll just stop here, just because it's kind of maybe interesting, since I've been talking about the intrinsics that have been developed in the API project. So you can see here an example of how the code for intrinsics with intrinsics looks like, and how the code that is then generated with the JIT ends up looking at. I actually know exactly for which function this is, but so you can see that in the case of intrinsics, you can still make use of variable names and do, for example, arithmetic on pointers, and then pass that to the intrinsics, will then generate the corresponding load instruction. But this sort of arithmetic that you can see, for example, in this first instruction, is something that you would not be able to do in the side of the JIT. Here, you have to have to pre-compute it exactly the value in order to be able to generate that. And all right. And switching a little bit to a different project that was also work that we have been looking at was to optimize the OpenMP for execution on the RISC-V. In fact, this was more started as a more generic. We started also looking into ARM SVE at the beginning and also into the Intel SIMD, but with a long-term goal to support RISC-V vectors. And so, well, here the problem where we focus specifically on synchronization constructs such as barriers and reductions in OpenMP. And as you know, the problem is that, well, if you look, for example, on this graph here, and where on the x-axis we have number of threads. This is actually run on a Intel KNL, and we look into sort of the overhead that results just from this operation. You will see that the more threads you add, the performance degrades. So question was, can we make use of vectors? Can we utilize vector units to reduce this overhead? And by the way, this Intel KNL was located at the HPC2N. So this is links. It's the one that you had. So we got access through it via SNCC at some point. Anyway, so, well, you know, this is supposed to be an example of a barrier. A barrier is a construct in which you have multiple threads that have to sort of wait all at the same place and wait for each other. And only when all the threads have arrived, then they are allowed to proceed. So one attempt to vectorize this is shown here on the right side. Let's assume all the threads, when they reach the barrier, they will activate a bit, which is a part of a vector. And then the primary thread can try to load this vector using a vector load, and then try to see if all the threads have reached. So very simple idea. Similar can be also applied for reductions. There it becomes a bit more complex because we have to apply the reduction, and we also had to modify Clang. But for the barriers, we did an implementation that was only inside of the LLVM OpenMP runtime. And we created 3 different versions, one for Intel AVX, one for ARM SVE, and one for the RISC-V vector extension. Now, the results that I have are only shown for the KNL machine and A64FX, because at that time we didn't have access to test still on the hardware for the RISC-V. But but what we did do for RISC-V is to validate that, because at that point we used an approach using this VHAVE tool, which is the emulator for the vector instruction, which I mentioned before, and that was coupled with Chemo. So Chemo is well, I will talk about it a bit later, but Chemo is basically an emulator for a system level emulator. Okay, so we did this result, and at least for the KNL platform, we observed that we could reach already a speed up, just launching barriers at this point of up to well, a little bit over 2x. So we haven't been able to test this yet on the EUPILOT prototype, but that's sort of one of the next steps. And based on that, we'll see if we can provide some feedback back to the hardware team on the performance of the barriers. Okay, I finish here with describing a little bit of things of more research-like that we have done in terms of RISC-V, and I will try to finish a little bit asking more a question or sharing some thoughts about how I sort of see the road ahead for RISC-V in terms of HPC. These are, of course, my own thoughts, and they are probably biased and faulty in extent. A lot of things are happening in parallel, in fact, in this field. It's difficult to keep track of everything. But what I can tell you is that, well, as you have seen, there's a lot of progress happening actually at all the levels. There's work going on from the hardware side, on the instruction set architecture, and also on the software libraries and tool chains. But I think there are challenges at all these levels that still need to be faced. So I want to talk a little bit about these things. It's going from hardware, ISA, to software, a few other thoughts, and then even share some thoughts. I mean, what you could do if you're interested, for example, to look a bit into RISC-V, or you in a general sense. Okay, so there are, if you want to, let's say, start with RISC-V hardware, there's actually a lot of small boards that implement RISC-V. But if you are looking specifically for HPC, it's a bit more difficult. So I try to, I mean, based on my limited view of it, of course, I haven't read all the papers and everything that is happening all the time, but I'm only aware of, let's say, one board, at least that I have seen having been evaluated independently, and that's this, this Sophon SG2042, which consists of a set of cores from a company called T-Hat, and this one is implementing the vector spec 0.7.1, so it's not implementing the 1.0. And I sort of highlight this independently evaluated here because I see that there's a lot of projects, and even I can see pictures of people saying, okay, we are developing this chip, and here's a picture of the chip, but I have actually not seen anyone use that yet or having it evaluated. But here there's a paper. In fact, this is by, I think it's by Nick Brown. He was discussing about this in the RISC-V workshop at supercomputing last year, where they looked into this system. One of the challenges is that this does not implement the last version of the vector spec, so it actually requires a custom GCC compiler. So from terms of usability, particularly for that vector instruction, it's actually not very convenient. But supposedly, it looks like there is there's light at the end of the tunnel. I would say there's a huge amount of companies, and many of these companies have a large amount of funding and backing that have announced or have publicly disclosed that they are working on high performance hardware. And often there are systems specifically targeting HPC and also systems targeting AI. So here, this is just a list of the ones that probably come to my mind when I prepared this slide. But it's companies such as Tenstorrent. They are developing a large out-of-order RISC-V cores plus an AI chip which is called a Tensix. There's Ventana Micro, which is also developing a big out-of-order processor with vector extensions. Esperanto Technologies, they have these two types of cores. They have some very small RISC-V cores that you call the Minion, and I think that's mostly for AI type of workloads. And they're also developing a host processor, the ET Maxion. Semidynamics, a company which is part of EUPILOT, they have developed, for example, out-of-order code called Atrevido. This has sort of an interface for a vector unit, and I think that they have their own implementation of a vector unit outside of the vector unit that I was discussing in the EUPILOT project. And they have also, in fact, a set of custom tensor instructions that they are developing for AI workloads. Inspire Semi has an accelerator platform which they call Thunderbird, and there are probably more. I think these are all companies. I mean, most of them are US companies. Semidynamics is, of course, located in Europe, but I'm sure that there are companies many other places in the world that are currently developing hardware. So at some point, we are going to get to the point that we will have more availability. But right now, I am personally not aware of any of these systems that can be accessed. I might be wrong, but I haven't come across that yet. The good thing is that all of them, from what I could understand, support the RISC-V Vector 1.0 spec, and that's good because once these systems become available, it should offer interoperability. You should be able to run code on one system. It should also be able to run on the other systems, and that's of course, very important for being able to, not only deploy software but also be able to compare systems. But later on we'll see, it will be very interesting to see once these systems become available, if it is possible to start running benchmarks on them to actually see how they compare in terms of performance. Now, what's going on in terms of specification? So I've talked a lot about the vector spec, and I think that's certainly a big step ahead for being able to support HPC in the context of RISC-V. Now, there is still a lot of discussion going on in the what's it called, the special interest group in the vector SIG in RISC-V. Luckily, everything in RISC-V is kind of open, so everybody can just go into the archives or the mailing list and see what people are discussing, what's going on, what sort of discussions for new versions of the spec are happening. What you cannot do unless you are a member is to join the meetings themselves and try to participate. For that, you need to first become member of the RISC-V International, which you can do as an individual or as an organization, depending on whether your organization is paying your work on RISC-V or not. But anyway, because of that, I have been able to attend some of these meetings and also look into lots of mailing lists to sort of try to understand what is currently being discussed. And here are some things that I've seen that are sort of topics of interest inside of the vector SIG. One is that there's a lot of interest in subsetting the current vector specification. What this means is that we now have a vector spec, but this vector spec is actually very large. It's actually, well, the last time I checked it, it has around maybe 200 instructions, and it's implementing it in its totality is quite complex. And particularly for embedded devices, you might not be interested in implementing the whole thing. So there is discussion, for example, in separating the vector specification into smaller sets. That probably hasn't too much impact on the HPC part itself, but what could have an impact is the next thing. So self-contained vector instructions. So RISC-V vector instructions are currently 32 bits, and that's not a lot of space to specify, many of the operations that are required for these vectors, particularly for this vector length agnostic design. So the vector spec currently is based on having a lot of control registers that support and that impact the execution of the instructions. But there is, there's a discussion on having a new version of the vector spec that would have longer vector instructions, maybe 64 bits, where all this information is encoded as part of the instruction. And that could, for example, enable having more architectural registers. Right now we have 32 vector registers. Maybe in the future, a future version of the spec would have 128 registers. And then, that will have a big impact on many of the applications. For example, the Vinograd implementation that I discussed, we were limited. We had problems of register spilling. If we had 64 or 128 registers, that probably goes away. Then other things they're looking at is some sparsity support and also trying to have more GPU-like capabilities in the spec itself. Other things that are, I think, very important, particularly for AI, is that there's a lot of interest in matrix extensions. And before we had a bit of this discussion about the customization, whether you need to give back any extensions that you make to the spec or not. Well, this is a field in which you will see a lot of custom extensions, because right now we do not have any standard extension inside of RISC-V. There are two working groups, one for what is called for the integrated matrix extension, which I understand. I think what this means is that it's a matrix extension that makes use of the vector registers for storage of the matrices, and then attached matrix extension, which would then be more like a coprocessor type of matrix extension with externally stored matrices on separate registers. So many companies are currently have developed their own custom matrix extensions for these types of workloads, but the natural flow should be such that at the end of the road, these extensions somehow converge into an actual specification. And another thing that I also highlighted here, I mean, I think there are more things in the RISC-V spec that impact HPC, but also I mean, personally, I've always had a big interest, and I think it's very important, the topic of performance monitoring support. So there is, I mean, RISC-V does have a spec for performance monitoring. But one thing that is going on now is that right now, the specification for performance monitoring just specifies how to access the counters, for example. But it doesn't specify which counters need to be available. So right now, there is a process to also have a specification of a set of names for standard performance counters. And I think that's also going to be very helpful because it will guarantee that we can, run PUPI or whatever, or perf on all these platforms and hope to get the same counters so that we can use the same performance tuning methodologies on all these platforms. So that's also hopefully something that is going to be there also in the future. I have only a couple more slides. I wanted to mention something about software tool chains. Obviously, for the success of RISC-V, we will have to port a lot of software. We have seen how long it took in the case for ARM to become competitive on the HPC side. Same sort of effort needs to be done in the case of RISC-V. I have discussed some of the work that we have done in EPI and EUPILOT. And here's just, I tried to go quickly over that slide that I showed earlier to highlight some of the libraries that we are actively working on and some of the tool chains. But there is more work. I mean, there's a big interest on this topic, of course. And in fact, there is an industry-led effort, which is the RISE project, which is the RISC-V software ecosystem. And they are looking about what has to be done in all these levels to try to accelerate the development of open source software for RISC-V. So looking as compilers such as GCC and LLVM, system libraries, SSL, glibc, BLAS, the kernel, mostly focusing, of course, on Linux and KVM, managed runtimes, Linux distributions, debug and profiling support, simulators, and system firmware. So a lot of things happening in that front as well. So some ideas more from our own experience working on RISC-V is that, while you might think, okay, it's just a new architecture, let's just recompile and we are done. This is, of course, far from it. One challenge, I mentioned this before, is that a lot of codes that we want to be able to run on RISC-V in the future on RISC-V accelerators are currently being developed, for example, only in a language such as CUDA. So there's a question, how can we make CUDA programs use RISC-V? Do we need to rewrite basically the application to use more like the vector way of programming with intrinsics, or trying to rely on OpenMP SIMD? Or maybe an alternative approach is to use automatic conversion from CUDA to something like SYCL. There are some tools that enable that, and then try to have a high performance implementation of SYCL. And there's some work going on there. So in the end, yeah. just point out that RISC-V is not a GPU, so those codes will still require some effort to be done. And in the context of EUPILOT, one thing that I see is that we were working on trying to do long vectors, but the way I see it, being able to fill long vectors is very much algorithm dependent, and a lot of code that, for example, has been developed with Intel, like SIMD, like x86 in mind, will not easily translate to very long vectors, because there you have more shorter vectors up to 512 bits. And when you know that and you program specifically for that, you will already organize your algorithms targeting that. You will not write your algorithm to be able to extract vectors of thousands of bits. So we will need to do some research into either more advanced compiler support to be able to fill these longer vectors, or at the end, the developers themselves will need to actually do some algorithmic transformations to expose the required parallelism to fill these long vectors. And yes, I guess I'm almost done. The one thing I also thought that maybe could be interested, if you have never come across the RISC-V, but you're a little bit curious, just to point out that there's a large amount of boards. These are mostly small boards, not HPC-like boards that you can play with. You can go to this link, and there's a long collection. Also, if you're a bit more interested in the HPC side or the work that we're doing in EPI or EUPILOT, I want to mention that these SDVs that I mentioned before with the FPGA and the Unleashed boards, that's actually open for external access. I think if you send an email to Filippo Mantovani, you can request access to that, and you can also play with that toolchain there. If you don't want, or you don't have hardware, or you don't want to have hardware, there are of course also alternatives. Spike is sort of the golden reference for the RISC-V ISA as an emulator. And if you want to do something that's a little bit more complete, QEMU is actually part. I mean, there's a lot of good support for RISC-V in QEMU. It's part of also of the goals of the RISE project that QEMU is well supported. And I think there's a commitment that all ratified instructions need to be in QEMU. So you can actually get quite a lot done by using just QEMU to start playing with RISC-V. And finally, this is maybe more interest of me, because we do a bit more computer architecture and performance evaluation. If you are in that field, then it's also good news that GEM5, since the last release in December 23, release 23.1, now also includes a model for that supports the Vector 1.0 standard. Okay, so that's I thought that would be all, but now of course I have a conclusion slide, and I have an acknowledgement slide too. So, well, we have seen a lot of progress. We are working in EPI EUPILOT, working on a multi-core system with vector support and a software tool chain. And there's also a lot of work at the community. As I said, I think that the vector is a big step forward for being able to have high performance computing based on RISC-V. But I think we'll need to have more boards, more HPC-like boards to play with and performance tools, so that we can start optimizing the code using more serious platforms. Yeah, we hopefully the HPC hardware will also converge around a set of more stable specs. And I didn't talk about something called the RISC-V profiles, but that's actually sort of the way RISC-V is trying to get vendors to focus on the same market to use the same set of vector extensions, so not vector extension of RISC-V extensions, so to avoid fragmentation. And well, I've talked about some specific challenges in this talk that I particularly think are interesting, at least for us, that we're looking at, is the auto-vectorization for extracting long vectors, or more systematic ways to rework algorithms that will allow to extract longer vectors. Also, conversion strategies to move from CUDA to be able to execute CUDA programs on RISC-V. And finally, I think it's going to be very important that the working groups that are defining the matrix extensions try to come up with some standards rather soon. Okay, so now just I wanted to acknowledge that of course all this work has been done by my team. We call ourselves sort of informally, we call that the CHAR team, Chalmers Heterogeneous Architectures Runtimes team. And yeah, and you always try to make just a plug here to just point out that we have also a very nice master program in high performance computing systems. And then if anyone is interested, then please come. Okay, I have absolutely no idea how long it took, but we're done.
We started late, but you're pretty much on time if you factor it in.
All right. Okay. Well, thanks. Thank you for enduring me until the end.
Want to take some more questions, maybe?
If there are any, I'll be happy. I'll be around in any case until tomorrow evening. So I think there's a question.
Well, so you said about the difference between an open specification and open source hardware. I didn't get exactly what is the difference.
In this case, open specification just refers to the instruction set architecture, to the language that the hardware has to talk. So you can take the specification, you can customize it, change and add new instructions if you want. And nobody is going to stop that. In that sense, it is open. But open source hardware would mean that, for example, you publish the RTL, the Verilog or HDL, like we are publishing the C code or C++, right? So that's sort of the difference.
You talked about emulation a bit as well through QEMU, for example, when you're playing around with RISC-V, since there's to some extent a lack of hardware to actually run stuff on. And in a previous RISC-V talk I saw is that it also depends where you're running QEMU in terms of getting a better emulation to some sense, or at least better, closer to the hardware. Like running QEMU on an ARM system makes more sense than running it on an x86 system, because the memory model of ARM is very similar, or is at least a lot closer to RISC-V than it is for x86.
I mean, what you say makes sense. I personally don't have that experience. I don't have the opposite experience. I simply haven't tried that, so I can't really.
Well, what he was warning about is that if you can pick, run QEMU on ARM, because then it's less likely that when you're just transferring your binaries, let's say, to an actual RISC-V platform, that you're then running into surprises there, which you're more likely to overlook if you're running QEMU on x86. So there's a factor there as well, at least.
No, I think I understand what this means. I mean, in x86 you have a stronger memory model that's usually called TSO, total store order, and in RISC-V and ARM you have a weakly modeled, a weakly ordered memory model. And if you have some specific algorithms that happen to work because of the TSO guarantee, it might be that running those algorithms on QEMU on x86 work on the RISC-V emulation, but actually don't work in practice. That could happen. I haven't.
Okay.
But it's an interesting question itself. I mean, how can QEMU itself remove those guarantees? But that's probably maybe too much to ask. I don't know.
Yeah, it would only lead to further slowdown, which is probably not what you want.
Yes.
You want to use the underlying hardware as much as you can. And I think it's just an important detail that people should be aware of. Like, if you can, just run QEMU on ARM.
Particularly if you are developing, let's say, like lock-free data structures or stuff like that, that would be very important. I think.
Okay. And another thing is that you had a slide with lots of open source projects that are starting to look into RISC-V or are being ported to RISC-V.
Do you mean the one on RISE?
Yeah, the one like indeed, where like OpenBLAS and all these things are mentioned.
Mm-hmm.
I'm not sure if you have any experience with that, but what's the situation like when a project like RISE gets in touch with these projects and says, we want to add support for RISC-V? Like, do they actually know what RISC-V is? I mean, for GCC, that's a given. They are,
well, my
they're so low
understanding
level
is
that they
that,
are.
well, I mean, the people in RISE themselves are doing the work.
But then are the projects also accepting their contributions? Do they understand why it's interesting to do that? I mean,
well, that's probably a question that I cannot answer, but
Yeah.
I would say, say why not? I mean, do you think? Well, do
So-
you feel that there are any specific concerns
Well,
about it?
the reason I ask is a couple of years ago, we had an online talk by the BLIS maintainers. So BLIS is like, it's an alternative to OpenBLAST, let's say, a BLAST layback library.
Yeah, actually, I think we
Yeah.
have it.
Yeah, BLIS
there
is
too,
there now, but when, I don't know how long ago this was, but I think it was 5 years ago when they gave a really in-depth talk on BLIS and everything they do to make sure you're getting good performance kernels and so on. And I asked them the question about RISC-V, and they had no idea what RISC-V was. Now that's 5 years ago. Things are very different today.
I mean,
But
but the people from Jülich, right? They're developing it, or
No,
no?
where are they? In Tennessee?
Tennessee?
Is it? Or no, or Texas? No, Texas, University of Texas, I think. Yeah. So that surprised me a bit, because if BLIS doesn't know about RISC-V, they're so low level, they're basically hand coding assembly to some extent. Well, and BLIS not really, they're trying to avoid that. But if they didn't know about it 5 years ago, then I wouldn't, I'm pretty sure that many, let's say, scientific applications currently, which are 3-4 levels higher, still have no idea what RISC-V is. And some of them at least should, like if you're touching assembly anywhere, you better know that this is coming, because it's going to take some effort to make sure you're being ported. And this is just an observation, and it's not a criticism or anything, but that's I think it's still a challenge. It's improving, but it's a challenge to explain to people that this is coming and why they should be aware and maybe try to prepare for it.
Yeah, no, I mean, I don't disagree. I don't really have, I mean, I would like to know myself how much awareness there is, because I live in this RISC-V bubble, and it's sort of something I think everybody knows about this, but then you go out. I mean, but here, for example, I saw that most people are aware of it.
Yeah.
But if you go out to some completely different community, it's a good question. But yeah, I mean, like for example, in these European projects, or the way it works is a little bit like, okay, we define a project, we try to select which are the key applications that we think are important, and then we sort of reach out to the responsible and try to explain why we think it's important.
Yeah.
I don't know if this works similarly in other communities, but at least this is one way in which we try to make this awareness. So it's right now, it's sort of in the responsibility of the RISC-V community to try to convince people. That's
and of course, the more projects know about it, it's going to snowball into bigger awareness, of course.
Yeah, at some point, that hopefully should be the case. Yes.
You didn't mention any timelines, but do you dare making any predictions on when we'll have, let's say, a proper
the top 500, or
yeah, let's say that. Yeah, that's an easy.
Okay,
it doesn't have
recording.
to be well, but by then it may need to be exascale to be on top 500.
Yeah,
it's very different. It's a bit of a nasty question, but is it?
No, I could try it. I mean. So I think my main challenge to try to answer this question is that, let's say, I don't really know how advanced all these players are. I know that they have, huge teams working on it, so they probably have the capacity to put the system there in a few years. But if I don't see the system and see some numbers from somebody testing it, it's very hard to understand what is the maturity really, because showing a chip, here's the chip, but what does that mean? But it could be, optimistically, maybe 2 to 3 years, if these people are really where they claim they are, or more pessimistically, I would say maybe 5, 6 years.
That's getting the actual chip. That doesn't mean you have a full.
Well, a system, but yeah, but
Yeah.
but I'm saying getting no, but at that point I would say that the chip should be
Having
should
everything
be
in place,
working.
let's say, so you can,
Yes.
if
Yeah,
you
yeah.
want to, you
If-
could build a big system. Yeah.
I mean, some of these players seem to be close to that, at least from what they say publicly.
I mean, Tenstorrent is not, it's a startup in some sense, but there's people behind this, like Jim Keller used to
Yeah,
work
I-
at Intel, AMD, pretty much everywhere. So he knows his stuff quite well. That doesn't
yeah,
mean,
I mean, many of these are very well-known people backing them. Also, Esperanto Technologies, so Dave Ditzel, I think, behind. I mean, and I don't know which ones, but they have huge teams in the order of hundreds of people working on that, and with a lot of funding also. Okay, why? And I mean, as one of the things that I pointed out here is that many of these, they have, some chips that are specifically designed for AI. So I think one of the reasons that they have big funding is because there's people who hope that they will be able to get some part of the cake that NVIDIA currently has. But maybe if they make good use of their money, they should be able to reach there in a reasonable period of time.
Mhm. Let's see. Maybe we can invite you again in 3 years from now, and then we can see where
I
we
can
are.
say that the update.
Yeah.
Thanks. I think one way forward is to build a cluster specifically for AI, because this is a buzzword. You get, as you quite rightly said, money for that, and demonstrate RISC-V is actually a decent, and you have to take it serious competitor. Because otherwise you've got this chicken and egg problem. We are interested in, but it is new technology and we don't have the funding to do it. And because it is new technology, we are not interested in buying it because it hasn't been proven it is actually good. Think about the Lumi project, for example, where they deliberately used GPUs from AMD. They had quite a lot of problems to actually port all of the software into it. And I'm pretty sure you will have similar issues with the RISC-V. If you see what I mean. I try to be positive, just to be clear.
I mean, many of these are sort of trying to do what you suggest, to try to build a demonstrator for AI. But because it's like that, I mean, if you don't have the hardware or can show that it works, you can't convince anyone to buy into it. I mean, yeah, and we are sort of trying to do the same thing, but for the HPC. The HPC does unfortunately not have the same budgets that the AI has. So that's why EuroHPC puts more of the public money into it, because that's otherwise you can't go there.
Yeah, I think we can wrap up here. Miguel is going to be around for more questions to the end tomorrow. So I guess we can grab a quick coffee and then just jump straight ahead to Simon stuff. Yeah, that's you. Yeah.